E-Physics class presented by Fatima Convent High School, myself, Dipali. Chapter 10, Light, Reflection and Refraction. We all are familiar with what is light now. What are the different terminologies associated with reflection of light? Now let us see how the images are formed by the various mirrors or the spherical mirrors and what phenomena occur due to reflection of light on spherical mirrors. We have studied about the image formation by plane mirrors. I hope you remember the characteristics of image formed by a plane mirror. Let us yet recall. We know that an image formed by the plane mirror is always virtual and erect, same distance, same size, laterally inverted and behind the mirror. And what are the characteristics of an image which we need to keep in mind when we talk about an image? So it should be either real or virtual. It should be either inverted or erect. It can be same size as the object or enlarged or diminished or highly diminished, and the position of the image where it is placed. These points are important while understanding the image formation. Now, image formation of a spherical mirror can be studied by two ways. One is by practical method and one is by ray diagram method, which we are going to understand in this chapter. We have studied about the image formation by plane mirror. You also know the nature, position and relative size of the image formed by them. How about the image formed by spherical mirrors? What can we locate the image formed by a concave mirror for different positions of the object? Are the image real or virtual? Are they enlarged, diminished or have the same size? We will explore this with an activity. So let us perform this practical and see how the images are formed. First, we will understand the image formation by a concave mirror and then by a convex mirror. Now, we have already learnt the way to determine the focal length of a concave mirror in activity 10.2. We understood how we get a sharp, bright spot of light you got on the paper. In fact, the image of the sun. The way a tiny real inverted image. You got the approximate focal length of the concave mirror by measuring the distance of the image from the mirror. Now, take a concave mirror, find out its approximate focal length in the way described above. Note down the value of focal length. You can also find it out by obtaining image of distance object on a sheet of paper. Mark a line on a table with a chalk. Place the concave mirror on the stand. Place the stand over the line just as its pole lies over the line. Draw with a chalk two more lines parallel to the previous line such that the distance between any two successive lines is equal to the focal length of the mirror. These lines will now correspond to the position of point P, F and C. We know P means pole, F means focus and C means center of curvature respectively. Remember, for a spherical mirror of small aperture, the principal focus S lies midway between the pole and the center of curvature. Keep a bright object, say a burning candle, at a position far beyond C. Place a paper screen and move it in front of the mirror till you obtain a sharp, bright image of a candle flame on it. Observe the image carefully. Note down its nature, position and relative size with respect to the object size. Repeat the activity by placing the candle A just beyond C, at C, beyond F and C, at F and between P and F. In one of the case, you may not get the image on the screen. Identify the position of the object in which the case. Then look at these virtual images in the mirror itself. Note down and tabulate your observation. We will see in the above activity that the nature, position and size of the image formed by the concave mirror depends on the position of the object in relation to the pole, focus and the center of curvature. The image formed is real for some position of the object. It is found to be a virtual image for a certain other position. The image is either classified, magnified, reduced, or has the same size. Depending upon the position of the object, a summary of this observation is given for our reference in table 10.1. Now, we can understand easily that at infinity, if you place the object, the position of the image will be at the focus, highly diminished, real, and inverted. Beyond C, between F and C, diminished, real, and inverted. At C, same size, real, and inverted. Between C and F, beyond C, enlarged, real, and inverted. At F, at infinity, highly enlarged, real, and inverted. And between P and F, behind the mirror, enlarged, virtual, and erect. You will understand this table very easily when you understand how to draw a ray diagram, which is the theoretical method to find the position of image. But let us understand this experiment further. Now, suppose we have taken a mirror which is concave mirror and placed it on a center of curvature of this mirror is marked as point C. Now let us take this concave mirror whose C is center of curvature. This is pole P and this is the focus. So the distance between C and P is called radius of curvature. Between C and P is radius of curvature, and between F and P is called as focal length. Now we try to see where the position of the image is. Now first is at infinity. So at infinity, which cannot be shown on this screen, but we can understand that the rays might be coming somewhere this way. These are all incident rays which will be reflected somewhere behind. After reflection, they move in a way where they meet at one place and they will meet at the focus. So, all the rays after reflection will be meeting at this point F. That is the focus or the point where the image is formed. This is what you will be observing when you do it practically. Now suppose you are placing the image at the object at beyond C, that is somewhere here. If the object is placed beyond C somewhere here, then the image will be formed with the incident ray, say two incident rays are moving. Will be formed somewhere here between C and F. You can see that in the table given. When the object is kept beyond C, you have the image formed between F and C, which is diminished and real and inverted, which can be taken on the screen. Now again, if we try to observe this third position, that is on C. If the object is placed on C, then the image will be formed on C and will be of the same size as the object, real and inverted. If we take the next position, that is between C and F, then the image will be formed beyond C and F somewhere here. This is how the image is formed. If it is placed at the focus, then the image formed will be at infinity. Which is much outside our screen right now. And if the object is placed between F and P, then we will get a virtual image behind the mirror, and which cannot be taken on the screen. And which will be highly enlarged, virtual and erect. So this type of image will be formed. So this table tells us if the object is placed at various positions, the position of image, the size of image and the nature of image. This is how we find the position, nature and size of image practically. Now in the next session, we are going to understand how to represent the image with the help of a ray diagram. For that, first we need to understand what is ray diagram. We can also study the formation of image by spherical mirror by drawing a ray diagram. Consider an extended object of finite size placed in front of a spherical mirror. Each small portion of the extended object acts like a point source. An infinite number of rays originate from each of these points. To construct a ray diagram, in order to locate the image of an object, an arbitrarily large number of rays emanating from the point could be considered. However, it is more convenient to consider only two rays for the sake of clarity of the ray diagram. These rays are so chosen that it is easy to know their direction after reflection from the mirror. The intersection of At least two reflected rays gives the position of the image of the point object. Any two of the following rays can be considered for locating the image. So let us understand what are the rules to be followed for a ray diagram. Now we understand what is a ray diagram. Ray diagram is just a method by which we try to understand and study the formation of the image by a spherical mirror. A ray parallel to the principal axis after reflection will pass through the principal focus in case of a concave mirror, or appears to diverge from the principal focus in case of a convex mirror. This is illustrated in the figure. Now it's very clear from the figure that when we talk about diagram A, that is of a concave mirror, and diagram B, a convex mirror, if the incident ray is parallel, after reflection it has to pass through the focus because it follows the law of reflection. The dotted line shows the normal, and I and R the angle of incidence and angle of reflection. Same way in the convex mirror, we know that the shining portion is this side, and so the ray incident will come this way, and after reflection they too have to diverge, and they seem to meet at the center of curvature at the focus after reflection. This is the normal. So, is this first step clear? So, if your ray is parallel, then it has to pass through the focus after reflection. In the concave mirror, it will appear to converge, and in the convex mirror, it will appear to diverge. Next rule is a ray passing through the principal focus of the concave mirror or a ray which is directed towards the principal focus of the convex mirror after reflection will emerge parallel to the principal axis. This is illustrated in figure 10.4. So, if the incident ray is passing through the focus, after reflection it will be parallel, just the reverse of the previous case. Same way, if the incident ray is passing through the focus, after reflection it will pass parallel to the principal axis, both in concave and convex mirror, but in one it will converge and in other it will diverge. A ray passing through the center of curvature will pass back on the same path, that is, a ray passing through the center of curvature of a concave mirror or directed in the direction of the center of curvature of the convex mirror after reflection is reflected back along the same path. This is illustrated in figure 10.5, A and B. The light rays coming back along the same path because the incident ray fall on the mirror along the normal of the reflecting surface. So, it is going this way through C. Incident and reflected ray are coinciding rays. So, you can see the arrows showing incident ray and reflected ray, incident ray and reflected ray. Now, the ray incident obliquely to the principal axis towards the point P, pole of the mirror on the concave mirror or a convex mirror, is reflected obliquely. The incident and the reflected ray follow the law of reflection at the point of incidence, point P, making equal angles with the principal axis. So, if it is passing through P, it has to come back making the same angle I and R, as according to the law of reflection, theta I is always equal to theta R. Same thing with the concave mirror and convex mirror. Incident ray, reflected ray. Incident ray, reflected ray. Remember, all this is also the above case, the law of reflection are followed. At the point of incident, the incident ray is reflected in such a way that the angle of reflection equals the angle of incidence. Now let us see the image formation by a concave mirror. Figure 10.7 illustrate the ray diagram for the formation of the image by a concave mirror for various positions of the object. Now you can see here at infinity is the object, you find the incident ray. We are taking only two rays for our convenience according to the law for drawing the ray diagram. We know if it is parallel, it has to pass through focus after reflection. So this is the point where the image will be formed. That is, if the object is at infinite distance, the image is formed at the focus, which is very small, real and inverted. We can see the properties. Here, at infinity, it is at focus, highly diminished or point size, real and inverted. We take the second case, that is when the object is kept beyond C. Again a parallel ray. It has to go through the focus after reflection. Passing through C, it has to go back on C. So you can see the point of intersection here and the image formed here. Now you can see the size of the image, what it is. First we need to see what type of image it is and how is the position of the image. So we can observe the position of the image beyond C, then it is between C and F. It is diminished, smaller than the object, real and inverted. Now next we are taking as the point C. So if it is passing through, incident ray is parallel, it has to pass through focus. If it is passing through focus, it has to be parallel. So we get the image and the object at the same position, that is at C. It is same size as the object, real and inverted. That is our next case. That is at C, same size, real and inverted. Now between C and F, between C and F means it will be forming incident ray, reflected ray, incident ray, reflected ray through C. It will be formed beyond C, inverted, real, and it will be little bit larger than the object. That is, at F, between C and F, it is beyond C, enlarged and real and inverted. Now next we are going to see at F. Now at F, the position will be, if it is parallel, again passing through F. If it is through C, back to C, but it will be formed at an infinite distance which is beyond the size of this page, and it will be what type now? Real and inverted and highly enlarged. And the last position we see between P and F. So if it is between P and F, it has to go parallel. If it is at P, again following the law of reflection, at C, then again at C. But it will form a virtual image which is highly enlarged and behind the mirror. So you can observe between P and F, behind the mirror, enlarged, virtual and erect. Isn't it very easy to remember this table? Yes, I'll give you a trick to remember this very easily. If you observe, at infinity is the first position. At infinity is the image here. Beyond C, at C, between C and F, between F and C, at F, and between P and F, behind the mirror, enlarged, virtual and erect. Only that is the odd one out. So if we just simply draw a ray diagram roughly for you to remember this, then it becomes very simple for you this way. C, F and P. At infinite distance, that is somewhere around here, if your image is, then it will be at F. At infinite, at F. As you move closer, that is at C, it comes still closer. So it will be between C and F, but it will be inverted. As you move still closer at C, it comes back on C. Can you see how the image is moving closer and becoming larger in size as we move closer? Then, if you still move closer here, it will go beyond C and it will be larger. Then, if it is at F, the object size remains same, but the image size goes on becoming wider and wider. It will go beyond our screen somewhere at infinite distance, and it will be highly enlarged. So do you understand? Position 1, position 2, position 3, position 4 and position 5. That is at infinite, then at F, beyond C, then between F and C, beyond at C, then at C, between F and C, then beyond F and C, and at F, then at infinite. These are the 5 positions, and you can see the image is always inverted and same side of the object. So the nature of image will be always real and inverted for first to 5 positions. This is the nature. Position we already understood, and size we know that as the object comes closer to the mirror, the size of the image becomes larger and larger than the object. So as the object moves closer to the mirror, the image will go beyond, away from the mirror, and it will become larger. Did you understand this very clearly now? So this is how you can remember the table very easily. But drawing ray diagram is not so simple. It has to be drawn technically, which I will be explaining in the next video. Now there is an activity 10.4. Draw a neat label diagram for each position of the object shown in table 10.1. You may take any 2 of the ray mentioned in the previous section for locating the image. Compare your diagram with those given in figure 10.7. Describe the nature, position and relative size of the image formed in each case. Tabulate the result in a convenient format. This activity we will be doing next time. Now we need to know the uses of concave mirror. Concave mirror are commonly used in torch, searchlights, and vehicle headlights to get powerful reflecting beam of light. They are often used as a shaving mirror to see a larger image of the face. The dentist use concave mirror to see large image of the teeth of patients. Large concave mirrors are used to concentrate sunlight to produce heat in solar furnaces. So do you understand how useful this phenomena and property of light is? And we are using it on daily basis. Thank you.